Let's continue for example 2.7. So in this case, we consider a charge distribution, a spherical charge distribution. And it's uniform distributed in this spherical region. And the charge density is rho sub-zero, which is a volume charge density. So as you can see, the units is coulomb over meter to the cube. So here you have a spherical region extending from r equals to 0 to r equals to a. So for r is smaller than a, you have a uniform volume charge density rho sub-zero. And for r greater than a, the charge density is reduced to 0. And you want to calculate the electrical field for this charge distribution. The electrical field includes the region within R, that is, for observation points smaller than A, and for regions outside of R, outside of A, outside of this charge distribution. So you want to write up the solution for electrical field intensity E for any given place. However, due to our understanding about electrical field and problem geometry descriptions, we know that the electrical field of this problem can only have R dependence because the problem geometry is spherically symmetric. 它是一个球对称的 source distribution， 所以它的电场只会跟 R 方向的 dependence 有关系，跟距离有关，跟 θ 还有 phi 是无关的因为球状对称的关系。So we can based on the problem geometry, we can guess the solution is like that. You can only have R dependence in the AR direction. All right? Now, what kind of Maxwell equation can we use to calculate this problem? Again, we will use the Gauss's law for the electrical field. Our Gauss's law for the electrical field. That is, here in this slide we see that based on the spherical symmetry of the problem geometry, we only have the electrical field intensity and electrical flux density only have the dependence on R, and it's pointing along the R direction. Again, we use the Gauss's law for the electrical field, which involves closed loop integral of closed surface integral of electrical flux in this spherical region, and the volume integral in this sphere, which equals to the well, I'll talk about that. Let's treat the surface integral first. Again, before carrying out the spherical integral, you need to write up the correct form for the surface, differential surface. So for this spherical surface, ds equals to what? Equals to r sine theta d phi times r d theta. And the spherical surface direction is pointing along the r direction. So combine these two differential lengths. This is the differential length along the phi direction. This is the differential length along the theta direction. And this is the normal direction of the surface. So combine the three, you end up with r to the square sine theta d theta d phi ar. Okay? And the integram The things to be integrated is the electrical flux density as written in here. So you simply put DRR with the differential surface. Note that the limit for the differential for the surface integral is for theta from 0 to pi, which direction is d equal to theta equals to 0. Is upward, is the positive z direction, and the negative z direction is theta equals to pi. And phi begins from what? Begins from x, positive x direction, and turn around for 2 pi radian. So if you carry out this integration is relatively simple because dr is a function of r. It has no dependence on theta and phi. So you can simply put this thing outside of the integration and simply made a surface integral for r to the square sine theta d theta d phi. And it should give you 4 pi r to the square. That is the surface of a spherical surface. So this is the area for a spherical surface with a radius of r. All right. So the left-hand side of the Gaussian law for the electrical field can be found as this. How about the right-hand side? Well, the right-hand side is simple as well. You simply carry out the because the charge density is a constant, it's uniform in this region. So you simply calculate the volume of the sphere, depending on the observation point. So now that there is a difference about the observation point, because if the observation point is smaller than the sphere, than the spherical charge distribution, then the electrical charge need to be accounted is less. It's only the ones that has radius smaller than r. On the other hand, if r is greater than a, which means that you are standing outside of this sphere of electrical charge, then all the electrical charge should be counted. So you have so if r is smaller than a, the charge to be accounted is 4/3 times pi r to the cube times rho sub 0. And if r is greater than a, then you get 4/3 pi a to the cube rho sub 0. One question that you should ask yourself is, because based on these descriptions, you found that even though the spherical charge distribution has uniform charge density everywhere in this sphere, and if you are located in this position, according to this equation, this calculation, this volume integral, you only account charge within the smaller sphere, right? Now, of course, we know that the charge, the electrical field produced by this orange sphere will have electrical field works on you. How about the rest of the charge? How about the charge in this region? Will they have effects on you? Will they produce electrical field on you on the observation point? 会吗？会有影响吗？答案是会，也是不会啦。答案是，假如你看说，这个地方的电荷对你有没有产生电场？有。这个地方对你的电荷对你有没有产生电场？有。 但是这些电场全部加起来，对你有没有有没有产生影响？没有。所以以前有一部电影叫啥，我忘记了。好了，成龙演的啦，好不好？可能超过15年了哈，所以各位大家应该没有印象。大概15、16年前，成龙有一部电影，然后他好像就穿越剧啦，就是说他变成一个秦朝的将军，然后跑到那个秦始皇的地宫还是怎么样，巴拉巴拉巴拉的哈。反正他进入地下了，结果进入地下之后，发现一个什么事情？他在里头没有重力啊，没有重力。好，重点不是成龙了 ，OK。好，换一个方式讲哈，有一些月球阴谋论嘛，有没有听过哈？你只要常看 YouTube 上面的那个说书人的话，有人说那个月球是一个空心的铁壳子啊，我们当然信不信我不知道啊。然后当然他们提出来一个证据，就是说你只要在那个月球上面摆一根那个咚咚咚的那个桩哈，然后你会发现它动一下哈，那个地震波会在那边响那个4、5个小时还是10几个小时，好像你在撞钟愣筋赶快哈，那个敲一下那边因为它是空心的嘛，所以它会在那边响很久。好，假设月球真的是一个空心的铁壳子好了，那你进到月球里面，你会发现什么事？没有重力啊。你感受不到月球的重力，为什么？因为那个铁壳子的质量虽然对于你会有各个部分会有重力的影响，但是它们的加总怎样呢？会等于0，所以这个是可以算得出来的，这个是可以算得出来，你可以证明，就是数学上面是可以算得出来，就是以这个重力。你用那个什么引力的关系式来算假如你是一个空心的球体的话，不管它上面的分布均不均匀啦，只要你是在内部的话，你的那个内部重力是等于0的。那同样的因为你知道重力关系式跟库仑定律的关系式很像嘛所以你只要去用库仑定律去计算的话，外面那边也等于0。OK， 所以希望能够解答你的一些疑惑。So you only need to account the electrical field produced by charge that is smaller than your observation point R. Okay, so the total charge that is effective toward the calculation of the electrical field intensity or electrical velocity intensity of the observation point can be divided in these two cases for R smaller than A and R greater than A. And of course, the total solution, that is, you divide 4 pi R to the right of the equation. You end up with dr can be divided into two cases. For R smaller than A, the amount of electrical flux density is proportional to R as R sub 0 over 3 times R. On the other hand, for R greater than A, then the electrical flux density is inversely proportional to the square of R. That is, rho sub 0 times A to the cube divided by 3R to the square. So you have two cases. And the interesting things, I found this problems quite interesting because you can express or you can exhibit the solution in terms of graph, which means 期中考很有可能会出现这种题目。OK， 大家都醒了哈。好了，我喜欢这种画图题啊。OK So this kind of to show this slide shows the solution graphically. So as you can see here, the problem can be decomposed into two sections. One is the observation is raising the sphere charge. So in that case, the electrical flux density is proportional, is linearly proportional to the distance r. On the other hand, if the observation point is outside of the spherical charge sphere, then it is inversely proportional to the square of r, like this. All right, so you should be able to draw the solution graphically. So that is example 2.7. Next is example 2.8. It's literally the same figure as you see in examples 2.7, but it's a complete different problem, all right? So this is a cross-section view, 横断面, cross-section view of conducting wire, which carries out a uniform current density of J, which equals to J sub 0 AZ, which means the current is flowing in the positive Z direction. So here you can see the coordinate is labeled as X, Y, and Z. Use your right hand to check up the correctness of the drawing, that is X cross Y toward the Z direction. And this illustration tells you that the radius of the current wire is A. And within this region, for R smaller than A, you have a uniform current distribution. That is J sub 0, and the direction of the current is in the positive Z direction. This must be a static current. This must be a static current because it's uniformly distributed. No. 我不知道各位你在做电路实验的时候有没有发现一件事情哈？你在做基础的电路实验的时候，假如你用的是单芯线，你通常使用的都是直流电源，但假如说你要处理的电路是交流电的话，那你去看交流电的电线你家那个你们家的那个电器的电源线你只要把它剪一段，注意要是坏的电器要是好的电器剪一段之后，你会被你爸扒头OK 它里面的线都是一捆的为什么？因为这个物理现象我们之后会谈到肌肤效应的关系所以当你的电流是交流电流的形式的时候，我想大部分同学大概有这个概念了。假如你是交流电流的时候，你的那个电流分布会靠近到那个导体的表面只有在 DC 的状况的时候，那个电流才会是均匀分布的所以假如你是 DC 电流的话，你可以用单芯线来去做因为电流的，因为电线的电阻是什么 ？R 等于 conductivity sigma 乘上距离 L 除以面积 A 嘛，对不对？那要注意这个电阻关系是只对直流电有效。只对直流电有效。假如你是交流电的话，那因为电流它就，因为直流电的话，你的电流是均匀分布的。假如你是交流电的话，那个电流就会集中到导体的表面。频率越高，分布就越往表面去。当频率够高的时候，基本上只有表面有电流。所以对于交流电线，为了要减少电阻，它就不会用一根实心的电线，而是一捆细的电线这样它的那个周长跟材料这样更有性价比了，好不好？简单讲就这样嘛你可以用这边，你可以用一捆的那个电线创造出比较多的导体表面，所以来去降低它的电阻。OK so one thing involved in this problem is that this kind of current distribution is only valid for static current. And in this case, we would like to calculate to find out the magnetic field inside and outside of this conducting wire. All right, we try to calculate H, the magnetic field intensity. Again, due to the symmetry of the problem, because the current is flowing in this direction, so based on the right-hand rule of Ampere, Ampere's rule, the electrical field is flowing in the phi direction for this geometry. H is in the phi direction, so we can write up H as H phi as a function of R, and the direction is in the phi direction. And it only involves R and no description about Z and phi is because the problem again is actually symmetric along the Z direction. So it has no dependence on Z and phi direction. 因为这个题目，因为这条导线是沿着 Z 轴摆放的，所以从 Z 轴的观点来看，它是一个轴对称的。那既然是轴对称的话，它在 phi 方向上面就没有 dependence。那因为这条线是无限长的，所以它在 Z 方向上面也没有 dependence。所以唯一的那个 dependence 在 phi 方 H 在 phi 方向上面，然后你的 H 的 phi 的大小是跟你离这条带电流导线的距离 r 有关系 ，OK？ So we get based on the problem geometry, we guess the solution is in this form. It's H phi as a function of r. So next we apply the Ampere's Kirchhoff law. And because we are dealing with the static field case, so the Ampere's Kirchhoff law is reduced from 3 terms into 2 terms. The time derivative of electric displacement flux d goes to 0 because this is a static case. So the closed loop integral of H equals to the what? To what? To the total current intercepted by the observation point. So you simply draw an imaginary contour C based on your distance R. So if R is smaller than A, you are simply drawing this circle labeled as red dash wire in this figure. So you calculate what you need to integrate is the total currents accumulated within this small circle. On the other hand, if R is greater than A, then you have a larger circle. Then the total currents accumulated or intercepted by this larger circle is the total currents flowing within this wire. All right? So let's carry out the left-hand side of the Ampere's Kirchhoff law first. That is the closed loop integral of H along this circular path. And you need to write out the differential length dl, that is r d phi a phi. So we know that you integrate along the phi direction, and because phi is an angle, not a length, so you need to times r. So r d phi a phi is your differential length. And the projected solution for H is in the form of H phi as a function of r in the phi direction. So if you can carry out this closed loop integral for phi equals to 0 to 2 pi, so you end up with 2 pi r H phi as a function of r, because H phi is only a function of r and has no involvement with phi, the variable d phi. So this integration is relatively simple as 2 pi r H phi. And the right-hand side is the total current intercepted by this circular region. So as you can see, it can be similar to the previous case. It can be divided into 2 cases. One is R smaller than A, the other is R more greater than A. So for R is smaller than A, the total current will be J sub 0 times pi R to the square. That is the smaller circular region intercepted by this imaginary red circle. And on the other hand, for R greater than A, you can have the total current as J sub 0 times the area, that is pi A to the square. And combining the solution of the two calculation toward integration, you end up with the expression for H phi, which can be expressed as J sub 0 R divided by 2 for R smaller than A, and JA to the square divided by 2R for R greater than A. So you have this result. And again, as I already mentioned, I would like to see the graphical representation for this solution. So you need to draw the solution for H. So it will be what? It will be a linear line for R smaller than 0 and curvature line for R greater than A. So you have this thing. So for R smaller than A, you have the H. The magnetic field intensity will increase proportional to the distance R. On the other hand, for R greater than A, it will be inversely proportional to R. All right. So that's example 2.8 for, and that shall conclude our discussion about section 2.